Good day, grade 12. Today we are going to look at a national senior paper, grade 12, 2025. So it's physical sciences, chemistry, paper 2 there, right? Okay, so let's just quickly go through the paper. So the first session there, we're going to have our instructions and all, then moving on to question 1.1, which is our multiple choice questions. So it reads here, which one of the following is the name of the functional group of propane 1-ol, right? So we can see propane 1-ol is an alcohol, and then the functional group of the name of these alcohols is referred to as a hydroxyl group, right? So we've got our option number 1, which says a carboxyl group, which represents our carboxylic acid, and then also you have our carbonyl group there, which is our ketones, and then option C there is our hydroxyl group, right? So this is the correct option. Then also D, we have got our formyl group there, which is incorrect, right? Then moving on to 1.2, it says here, the organic compound C2H4 is converted to an alkane as shown by the reaction below. Then it says here, which one of the following is a suitable catalyst for this reaction? So here they're saying which one of the following is a suitable catalyst for this reaction, right? So A, we have got our lead there is not a metal. We're not looking for this one. Then our platinum there is used as a catalyst. So it can be a PT, it can be a PT, like that, right? So those are the catalysts that we're looking for. All these are incorrect. So our correct option is going to be our platinum. Then moving on to 1.3 says, which of the following statements always apply to compounds that are structural isomers, right? So structural isomers of one another, right? So the first option there says here, they belong to the same homologous series, which is incorrect. And then they have got the same structural formula, right? So remember, the structure should be different than same molecular formula, but different but structural formulas, right? Then here option 3 says here you have the same molecular formula, right? So it means here the only option there that we're going to have there is going to be our A only. So this is the only correct option there. Moving on to question 1.4 is the magnesium ribbon of mass 2 grams. So given the mass of 2 grams reacts with excess hydrochloric acid of concentration 1 mole per dm cubed at 20 degrees Celsius. Then we're having this equation there that we're given. Then it says here, which one of the following changes will not increase the initial rate of reaction, right? So now we need to understand what really affects the rate of reaction there, right? So now I can put concentration, I'll say concentration, I'll say comma, temperature, then also I'll talk about what surface area, right? So these are some of the factors that affect our rate of reaction, right? So in terms of here, our A there is there using 2 grams of powder magnesium, right? So this one relates to surface area, therefore is incorrect. Also take note there, they are referring to not increase, so they've got no impact. So B there, it says increasing the temperature, so we already mentioned temperature affects it. And then option C there is there using a longer piece of magnesium ribbon, right? So here it means you're also talking about surface area. Then here D says doubling the volume of what hydrochloric acid. So this one is going to be the correct option there. Then moving on to 1.5, which reads the following reaction reaches equilibrium in a closed container. Then we're having HS, hydrogen gas, plus sulfur to give us H2S, like that. Then our delta H is less than 0, which is an exothermic reaction there. So it says the reaction rate versus time graph for the reaction is given below. So we're given the reaction rate versus time graph here, and then they're saying what change was made to the system at T1. So we're focusing at T1 there, right? So let's look at our options there. It says here the pressure was increased, right? So an increase in pressure will favor the side with the least number of moles, right? But if we can look here, we're having this gas and then this gas here, so it's 1:1, right? So it means if we increase pressure, it will favor both the reactants and the product sides, right? So then the pressure was increased at a constant temperature. This A there is the correct option there. I can proceed to B to say the volume of the container was increased. So increasing the volume of the container, it means decreasing the pressure. Therefore, we're expecting this graph to go downwards. Then see here, they're saying temperature was increased. So take a look at the type of reaction there. It's an exothermic reaction, right? So if you increase the temperature, it means now the reactants, the products, we're actually going to have to go down. We are going to favor the reverse reaction. Then after that, more hydrogen was added to the system. This one is also what? Incorrect. Then moving on to the next option there, question, which is question 1.6. A hypothetical endothermic reaction is given below. So this is an exothermic reaction that is given. So we're having A plus B to give us AB there. Then the activation energy for the reverse reaction is 50 kilojoules per mole, right? So we're given the activation energy for the reverse reaction there. They say which one of the following is possible for the reaction above, right? So now we're having our option A there that says the heat of reaction is a positive 70 kilojoules per mole. Then we're also having B there that says the activation energy for the forward reaction is 50 kilojoules per mole. The activation energy for the forward reaction is 50. So this is your EA there, 50 kilojoules per mole. Okay, then C says here the energy of the activated complex is 40, which is incorrect there. Then the activation energy for the forward reaction is also 40. These ones are incorrect, right? So now there is a possibility here. So they're saying the activation energy for the reverse reaction is 50 kilojoules per mole. Then the heat of reaction is, it can be 70, right? So remember your delta H there, your delta H is equivalent to H products minus your H reactants, right? So there is a possibility we can get what? A 70. So A there is the correct option. Then moving on to 1.7 there, it says here the products for the reaction between a metal oxide and an acid. So if we add a metal oxide and an acid, your product will always be salt and water there. So option A is going to be the correct option there. It says salt and water. All these, we do not have that one. We do not have that carbon dioxide. And then we also don't have that one. So our only correct option there is going to be option A. Moving on to 1.8, we're given the concentration of each of the four solutions below is 0.1 mole per tm cube. Then this is HNO3, then NH3, then we're having sodium hydroxide and H2CO3 like that. Then which one of the following correctly places the solution in order of increasing pH, right? So we need to look at the increasing in what? In pH, right? So it means now if we're increasing pH, it means the solution is becoming more and more basic like that, right? So in terms of this, we're going to have HNO3 is the first one there. So HNO3 is going to be the one, HNO3, the one that is stronger. So this is going to be number one. Then according to this list there, this one is going to be my number two, H2CO3 there, right? So you can see it's more of like it diprotic, it can donate to that one, right? Then after that, now we're having NH3 is our option 3. Then the last one, which is more basic, right? The strongest base there is our sodium hydroxide, right? So according to this list there, we're going to match with A is incorrect, then B starts with HNO3, then followed by H2CO3, then NH3, then your sodium hydroxide. So our option B is going to be the correct answer. Then these rest are incorrect. Then moving on to question 1.9 says a galvanic cell consists of the following half cells, right? So we're given the first one and the second one. Then which one of the following statement is correct for this cell, right? So they're saying Ni is reduced like that. So for it to be easier, we need to go and consult our reduction potential tables, right? So let's look at Fe3 at the bottom there. Fe3, so Fe3 there, let's look at our Fe3. So Fe3, and let's check there. Okay, so we're having this one there that is positive 77, right? So positive 0.77. I'll quickly scroll back there. So we're having this one there is a positive 0.77. Oh, okay. So it's Fe2 plus and Fe3 plus. Let me just check Fe2 plus and Fe3 plus. Fe2 plus and Fe3 plus, that's the one, right? Then also we're having our Ni as the second one. So our Ni there, you can see this is what we're having. So it's a negative 0.27. So I'm going to proceed and go back at the top, negative 0.27. negative 0.27 there. So this one is going to be a negative 0.27, right? So according to this now, we know how this is supposed to apply. So our anode there is going to be the one that is more negative, right? So it means this side we're going to have our Ni, and then the one that is more positive there is going to be the cathode, right? So it's positive 0.77, then this side we're having our negative 0.27, right? So this means here we're going to have our what? Our Fe there, right? So in terms of this here, they're saying which one of the following statement is correct for this cell, then Ni is oxidized, right? So this is the anode, right? So anode, at the anode, what happens there? Anode there, oxidation takes place, right? So oxidation takes place at the anode. So in terms of this here, we know Ni is reduced. So this one doesn't happen here. It actually happens what? At the cathode, right? So here we're going to have our cathode, and we expect to have what? A reduction, right? So reduction like that. Then now proceeding to the next one, says Ni is oxidized and Fe is reduced, right? So this one matches, right? You can see our Ni will undergo oxidation, then your Fe is going to what? Fe3 plus there is going to be what? To be reduced. So our correct option is going to be B there. Moving on to the next one, PT and Ni, all these others are going to be incorrect. Moving on to 1.10 there. So 1.10 is there. The setup for electroplating an iron metal with silver is shown in the simplified diagram below. Then we are having our iron metal, then we are having our silver rod there, then the electrolyte that is provided, and then also what? A power source, which is more of a battery. Then there, that's our iron metal, which is supposed to be what? Electroplated, right? So they're saying which one of the following combination for the anode and the reaction at the cathode is correct, right? So we're looking for the anode and then also the reaction at the cathode, right? So if we were to look at the anode, right? So the one that we're supposed to electroplate, the things electroplating there. So the one that we are supposed to electroplate there will always be the cathode, right? So this is the cathode, right? So the cathode there. Then the one that is electroplating the other is going to be our anode, right? So if we were to look at our options there, they're saying anode there is the iron metal. Okay, so iron there is the silver rod is the anode, right? So according to this, our silver rod there is the what? Is the one, right? So I'm going to tick this one, and then these ones are incorrect. Then the next thing that you're supposed to look at there is what? The reaction at the cathode is correct, right? So now it means now we're looking for this iron metal. What is going to happen there at the iron metal, right? So it means here there's going to be what? A gain of what? In terms of these electrons are going to move to it there, right? So in terms of that, it means now our D is going to be what? The correct option. So 1.10 there, D is the correct answer. Then moving on to the next one there, what? Question 2. So question 2 says here, A to G in the table below represents organic compounds. Then we're having all those organic compounds. So if we're to proceed there, it says here, which of the, write down the letters that represents each of the following, right? So we're looking for an alcohol, right? So according to this, an alcohol there is going to be option, let's look at this there. So this one might look like an alcohol, and this one might also look like an alcohol, just to cross check there. So here I'm having 4 carbons like this, 4 carbons like that, and then an O, right? So it means here I'm going to say hydrogen, since I'm having 10 hydrogens there, I'm just going to quickly add them like that, hydrogen, then another hydrogen, right? So if you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, then I'm supposed to have an OH there. So it means our option there for the first one is going to be letter D, right? So moving on to 2.1.2 says 2 compounds that are functional isomers of one another, right? 2 compounds that are functional isomers of one another, right? So now same molecular formula but different functional group, right? So if you can look at this there, what do we have there in terms of this? So we're having C3H8 and then also our pentane there, right? So if we're to compare these, what are we going to get there? If we're to compare these, what are we going to get there? So you can see E and F, all of them are going to be alkenes, right? But if we look at our A there, we can see that functional group there belongs to what? To a ketone, right? So this is a ketone, right? So if we were to formulate this one, you'll find that this O at the end there is going to formulate a what? An aldehyde, right? So it's going to be an aldehyde. So I'm going to say aldehyde for this one. So aldehyde, right? Therefore, it means our A and our C are going to be our functional what? Isomers. So now I'm going to say A and C like that, right? Then moving on to 2.1.3 reads two compounds that belong to the same homologous series. Two compounds that belong to the same homologous series, right? So it means now if you can look, already I mentioned E and F being all alkenes, right? So I'm going to say our answer there is going to be E and F. So E and F like that. Then moving on to 2.2 says here 2.2.1, write down the IUPAC name of compound A. So we're looking for the IUPAC name of compound A, right? So let's go back to our compound A. So we already know this is a what? This is a ketone. This is a ketone. So if it's a ketone like that, so now we're going to do something like this. Let's start by numbering there, right? So remember, we're going to start numbering from the side closest to the functional group, right? So it means this one is going to be carbon number 1, 2, then 3, and then carbon number 4, right? So what does that mean? It means on carbon number 3, we've got what? A side chain or a substituent there. So I'm going to say the name there is going to be 3- methyl, right? So since we're having only one carbon on the end, then after that now we're supposed to identify the longest chain. So the longest chain is 4 carbon, which is but. Then I'm going to say butane dash on carbon number 2. That's where we are having that double bond, or that formulates our what? Our functional group. So it means the final name, the IUPAC name is going to be 3-methyl butane 2-on, right? So like that. So then moving on to question 2.2.2 says the IUPAC name of compound B. So we're going to go back again to compound B there. So now we're supposed to number from maybe I can number from both sides so that it makes our lives easier. So I'm going to say this is number 1, this is number 2, 3, 4, 5, 6, 7, right? So if I number like that, it means my longest chain is going to look like that. Then if I number from this side, 1, 2, 3, 4, 5, 6, 7. Still, we can see 1, 2, 3, 4, 5, 6, 7. The longest chain is going to be what? Is 7 carbons there, right? So on after that now, we need to understand where we are finding our side chains, right? So you can see here what we have here. I can say here we're going to have this chloro, and then here also this is going to be our side chain, another one. Then here also we're having another chloro. So it means there we're having another chloro. Then where else are we going to have another chloro? On this other carbon there, right? So these are the carbons where we're going to have our chloros, right? So our side chains. So now in terms of this, I'm going to count using 1, 2. So on carbon number 2, if I can say carbon number 2 and number 6, using the blue one there, the blue ink, I'm going to say on carbon number 2, what do I have there? I'm going to say 2, 6, and then 2 and 6. This is carbon number 2, and that carbon there at the top, which is 6. What do I have? I'm having 2 chlorines, right? So I'm going to say 2.6 dichloro. Then after saying chloro, then I'm going to proceed to my methyls, right? So I'm going to say dash. Then on carbon number 2, also I'm having another methyl. Therefore, I'm going to say 2, then comma, and then on carbon number 5 also I'm having another methyl. So I'm saying 2, 5. Then after that, how many are these? There are 2 of them. So I'm going to say dimethyl. Then the longest chain there is going to be what? 7. So 7 is hept. So I'm going to say heptane because it falls like under the what? The haloalkanes there, right? So that's our correct IUPAC name there. Then moving on to question 2.2.3 again. So it says here IUPAC name of compound G, right? So we're looking for the IUPAC name of compound G, right? So let's look at compound G there. So in terms of our IUPAC compound G there, we're supposed to number again, right? So we number starting from the side that is closest to the functional group, right? So that double bond there, it makes it a what? An alkane, right? So I'm going to number maybe from here 1, 2, 3, then going down, I think 4 or 5, 6, it makes sense, because if I go this side is 4 and then 5. So I can also start numbering from there, 1, 2, 3, 4, 5, 6. So the longest chain is going to be 6 carbons, right? Then after that, now we need to find where we are having these substituents or these side chains, right? So in terms of this here, where do we have that one there? I'm going to count from this straight here. So it means this one I'm going to consider it as as a side chain, and then as I branch here again here, I'm going to consider this other part as a side chain, right? So in terms of this now, it means on carbon number 2 and on carbon number 3 I'm having a side chains, right? So in terms of this, on carbon number 3 I'm having an ethyl, and then on carbon number 2 I'm having an methyl. So in terms of this here, we're going to use alphabetical order. So it means ethyl comes before methyl. So I'm going to say 3 dash ethyl, then after that ethyl I'm going to say dash again, then 2 dash. Where do we find this methyl group? On carbon number 2. So on carbon number 2, what we have, we're having a methyl there. So I'm going to say methyl, then the longest chain is 6, which means now it's hex, right? I'm going to say hex. Then also I need to identify where we find this double bond, right? So this is the first one bond, and then this second bond. So I'm going to say dash 2 dash, then it's an alkene. Therefore the suffix is going to be what? ENE. Then moving on to the next question, which is 2.2.4. They're saying write down the structural formula of a 2 straight chain positional isomers of compound D, right? So let's look at our compound D. So compound D is our alcohol there, right? So now in terms of this, we are saying here structural positional isomers, right? So it means our positions are going to be different, right, from that one. So I'm going to write something like this. I'm going to say how many carbons do we have already? We're having 4 carbons. Then I'm going to change my OH group there, right? So I'm going to put it there like that, hydrogen, then hydrogen, and also hydrogen, and then the other one there, hydrogen, hydrogen, then hydrogen, like that, okay? Then on the other end also, maybe I can formulate something that looks like this. So I'm going to start with carbon again, 2, 3, and then the fourth one there, then put this OH on this other end, right? Then the rest there are going to be my hydrogens like that. So hydrogen, hydrogen, proceed, add those hydrogens. Remember, your carbon will always bond how many times? 4 times like that. So this is what you're going to have there. Then moving on to the next question, which is now question 2.3. So question 2.3 reads here, what do we have there? It says compound E, which is this one, C3H8 gas reacts with oxygen gas, right? So our oxygen gas according to the balanced equation, right? So we're having that and that to give this carbon dioxide, and then our H2O gas, right? So initially here we're given 8 cubic centimeters of this. So we're given our 8 cubic centimeters of that. Then after that, now what does it ask? It says compound E, initial 8 cubic centimeters of compound E and 50 cubic centimeters of oxygen were injected into the container, right? So if these were injected into the container of adjustable volume and allowed to react, right? So now they're saying write down the name of this type of of reaction, right? So the first thing that we need to look at is the type of of reaction, right? So according to this here, we can see our products are carbon dioxide and water. So it means here it's a combustion reaction, right? So it's a combustion reaction, right? Combustion reaction, right? So to be specific, maybe I can say complete combustion, but because now we're having our product as what? Carbon dioxide, right? So that's how we go about that one. Then moving on to 2.3, okay, I can just say maybe put the complete combustion there. So now 2.3.2 is there. So it says here calculate the total. So we're looking for the total volume of the gases present in the container at the end of this reaction, right? So in terms of this there, now what I'm going to start with is the ratio between CH3 and our oxygen, right? So in terms of this, I'm going to say CH3 H8 versus our oxygen there, right? So our oxygen, then according to this ratio there, you can see is 1:5, right? So I'm going to say 1 this side, and then on this other end I'm going to say 5. So our ratio there is going to be 1:5, right? So this is in terms of of the volumes there. So the volume that is used here is 1, and then on this other end I'm going to say 5, right? So after that, now I'm going to say, what about if we use in terms of our volumes there 8 cubic centimeters this side? How much are we going going to use on this other end of oxygen, right? So to find that one there, I'm just going to bring that one down there. Therefore, it's going to look like this. So it's more of me saying 5/1. So it's going to be 5/1 multiplied by that 8 there, right? So if we're to do our math, we're going to get a value of what? Let me just like quickly punch it there. So I'm going to say 5/1 5. Oh, it's more of like 5 times 8. 5 times 8, which is equivalent to what? To 40. So it's automatically, I'm going to say this side, we're going to get a value of what? A volume of what? 40 cubic centimeters, right? Then moving on to the next one there. So the next question there reads okay, the next part, what we need to do there is like to find how much of this oxygen is available, right? So in terms of this here, we're given the oxygen. So the oxygen that is available there, and compound E, and 50 cubic centimeters of oxygen, right? So the available oxygen is what? Is 50 cubic centimeters, right? So I'm going to say like O2, then available, then I can just like say maybe available there, so that we can easily follow, is equivalent to how many cubic centimeters we're given as 50 cubic centimeters, right? Therefore, now in terms of the oxygen that is in excess, right? So oxygen is in excess. Now we're going to say, look at this. Now what we need is 40 cubic centimeters, but what do we have? We have got 50 cubic centimeters, right? So what does that mean? Therefore, our oxygen is in excess, right? So what does that mean? If our oxygen is in excess, it means our CH3H8 is the one that is the limiting reagent, and therefore it will determine the amount of what of product that is going to be what to be formed, right? So now I'm going to say CH3 is the limiting reagent, and then it is therefore going to be completely used up, right? So now oxygen in excess, let's find the amount of oxygen that is in excess, right? So I'm going to say O2 in excess. So how much of this oxygen is in excess, right? So we're saying we only need 50, and how many do we only need 40, and how much do we have? We're having 50 there. So it means now I'm going to say 50 minus 40, therefore it will give me a value of 10 cubic centimeters, right? So this is the volume that is in excess, right? So take note, they said calculate the total volume of the gases present in the container at the end of this reaction, right? So I'm going to say 10 cubic centimeters. Then after that, now I'm going to proceed also to look at our equation. So now I'm going to say, let's look at that equation. So it was C3. I'm going to compare C3. So I'm going to say C3H8, and then to give us what? So to give us the, on the other end, what we have? We're having 3CO2. Then also I'm going to say plus what? 4H2O, right? So then after that, now I'm going to say here what we had for 8 cubic centimeters, what are we going to get, right? So in terms of this, how much do we have already? We're told is 8 cubic centimeters, right? So now I need also to find the one for carbon dioxide and the one for what? For H2O in form of what? Of a gas, right? So now I'm going to focus on our CO2. I'm going to say CO2 formed there. How much of it was formed, right? So remember, the one that is going to determine how much was formed is this C3H8, because it is the limiting reagent, right? So in terms of this, how much do I have here? I'm given a value of what? Of 8, right? Then I'm going to multiply by what? By this 3 there for what? For carbon dioxide, right? So what am I going to get there? If I multiply 8 times 3, I'm going to get a value of 24 cubic centimeters. Then I'll do the same for H2O there. So how much do I have there already for C3H8? I'm going to have, I'm saying I'm having 3, then multiplied by how much of this is equivalent to what? To 4, right? So if I do the math again, I'm going to get a value of what? Of 32 cubic centimeters. So it's going to be 32 cubic centimeters, right? So now what I'm supposed to do is to calculate the total volume of the gases present in the container at the end of the reaction, right? So total there, I'm going to add all these values, right? So I'm going to say this is equivalent to 10 plus my 24 there, plus 24 plus the last one, which is 32, right? So if we are to do our math there, I'm going to get a value of what? Of 66. Yes, I think it's 66 cubic centimeters, right? So you can convert it to dm cubed if there is any need there. Then moving on to question number 3. So question number 3 there reads, the two bottles contain A and B, contain compounds A and B with the same molecular formula of what? This is the same molecular formula of C4H P.2, right? So now they're proceeding to say here, these compounds are straight chain organic molecules that belong to two different what homologous series. So we've got two different what homologous series, right? Then after that, it says here the boiling points are used to distinguish between the two compounds, right? So now the first thing they're asking us is to define the term homologous series, right? So this is a group of compounds, a group of compounds, a group of organic compounds, compounds, organic compounds that can be defined by the same general formula. Like that. Okay. Then now moving on to 3.2, it says identify the two omega series to which these two compounds belong, right? So if we are to look at these ones, the general formulas there in terms of that, right? So we need to look at them. There is CH4HC4 H8O2, right? So generally the ones that have got like two oxygens, we now know it's going to be what our carboxylic acids. So I'm going to say carboxylic acid, and then the other one is going to be what our ester, right? So these are the only ones that have got what two oxygens within their chain, right? Then after that it says the following are the vapor pressure of these compounds are given. The following are the vapor pressure of these compounds at a given what temperature, right? So we're given the vapor pressures of this, right? Then compound A, there is it's got a pressure of 0.7 0.071 kilopascals. Then compound B, there is got this one, right, which is 9.7 kilopascals, right? Then write down the structural formula of compound A, right? So how do you determine A is which one, right? So here we can see our A has got the lowest vapor pressure, right? So if it has got a lower vapor pressure, it means it has got what a higher boiling point, right? So in terms of this, the one that is going to have a higher boiling point is going to be what our carboxylic acid, right? So in terms of this one now, this is our carboxylic acid. It means it's going to be our A. And then in terms of this, we are told this carboxylic acid has got, carbons is total of 4, right? So I'm going to put them 4 there. Then after that, I'm going to put my hydrogens like that, hydrogens. Then after that, it's supposed to be a carboxylic acid. So it means I'm adding more again there like that, right? Then I'm going to say double bond, then I'm going to say OH like that, right? So if you can count your hydrogens, you find you're going to have a total of 8, 1, 2, 3, 4, 5, 6, 7, 8, and 2 oxygens there. So that's how we focus on compound A there, right? Then the IUPAC name for a possible compound B, right? So for it to be easy, again, let's just like draw this one. For an ester, it means here I can say our C there. So if I'm having a C there, I can formulate maybe something like this for an ester. So then after that, I'm going to say an oxygen, then I put a C again there. So what do I have there? I'm going to say double bond O, then how many? 2, 3, I'm now having total of 4 carbons like that, right? So then after that, I'm going to put something like this. So this is the structure that I formulated there, right? So in terms of this, now if I can name this one in terms of the IUPAC name, there I'm going to say what do I have in terms of an alcohol, right? So it's meth, so it's going to be methyl, then 1, 2, 3 carbons. I'm going to say methyl propanoate like that, right? So that's how we go about that one then. So we're done with question 3.2. Now moving on to 3.4, it says write down the strongest type of van der Waals forces between the molecules in compound A. So compound A, remember, is our carboxylic acid. So it means now the type of van der Waals forces O. So now in terms of the van der Waals forces, we should take note there. Let's just say the one that is strong, we're actually going to say what if the strongest force there, without mentioning anything, we're going to go forward for hydrogen bonds, and then the other one was going to be what dipole forces, right? So the dominant force here is going to be what our dipole force there, dipole, so dipole forces, right? So dipole, so it's an example of what? Of a van der Waals, right? So also on the other one there, we're also going to have what? The one that is dominant there is going to be what? Our dp there, right? dp like that. Okay, then moving on to 3.5. So 3.5 there reads, which or compound A or B has a higher boiling point? Give a reason for the answer by referring to the strength of the intermolecular forces, right? Automatically we know it's going to be A. Why? Because now our A is going to have what? Hydrogen bonds. A has hydrogen bonds, right? So by referring to the strength of the intermolecular forces, right? So hydrogen bonds, and then we know we're going to conclude by saying hydrogen bonds, H bonds are stronger than dipole forces, right? So I'm going to just write dp there, dp, right, for dipole forces. Then moving on to 3.6 says the boiling point of compound A is measured again on another day when the atmospheric pressure is much lower, right? Then how will the boiling point of this compound now be affected? Choose increase, decrease, remains the same, right? So in terms of this, what is going to happen there is that we're looking at another day where the atmospheric pressure is much lower. So remember, the lower the pressure, it means the higher the boiling point, right? So there I'm going to go for increases then. Then moving on to question 4.1. So it says that the three organic reactions 1, 2, 3 below. Compounds T and W are organic compounds. I and S are organic compounds there, right? Consider only the major products. So we're going to focus only on the major products, right? So it means here 4.1.1 is there. Write down the IUPAC name of the compound W there, right? So in terms of this, we're going to look at W there, right? So for it to be easier, we're going to say, what are we going to have there in terms of our 4.1.1 there? Okay, there what we are going to do there is to put our HBr, right? So I'm going to say this one there is our HBr, right? So they're saying W there. So W, in terms of W, if we can say that one is our HBr. So if we were to look at this, right, so it means here, to make it easier, let's look at the one at the bottom there, right? So let's look at the number of carbons that we're given here is 1, 2, 3, and 4. So we're having 4 carbons there, right? So in terms of this day, we're going to say, remember, we're going to start with something that is more of saturated on this other end in terms of my T, right? So allow me to just like maybe formulate the structure of this one, write down the structure of each 1, 2, 3, and then maybe double bond there 4, right? So this is what you're going to have there. Then after that, now I'm going to put my hydrogens and all, right? So I'm going to put a hydrogen there, another hydrogen, then at the top there hydrogen 3, and then this one 1, 2, 3, 4 is now enough, and then I add another hydrogen there plus another hydrogen, right? So take note here at the bottom there is another hydrogen, right? So this is our T, then it's supposed to give us our W, right? So in terms of this, we are going to overcome that double bond, right? So we're going to now have a single bond like that. So this one is going to be our H, and also take note they said we should only focus on the major product, right? So in terms of this, Markovnikov's rule says the hydrogen is going to attach where there are more of hydrogens, right? So it means our Br is going to be there, right? So it means now we've got this W there. This is the one. So I'm going to just like write it down here. So the IUPAC name, so they are asking in terms of the IUPAC name for W, right? So the IUPAC name is going to be 122-bromo. I'm going to say 2-bromo. Then after that, the longest chain there is 4 carbon. So it's going to be what? Butane. So I'm going to say 2-bromo butane. The name or formula of what? Of R. So we're looking at the name or the formula of what? Of R there, right? So it's 4.1.2. So take note, we're starting with this one there. Then look there is no HBr. So it's going to be our HBr there. So I'm going to say HBr like that, right? Then 4.1.3 says 2 names of the type of reaction in one, right? So we're looking at reaction number 1. So in terms of reaction number 1, what do we have there? So it's going to be the type of reaction there. What did we start with there? We started with something like a double bond there, an alkene, right? So I'm going to say it's an addition, right? So I'm going to say addition reaction. Then after that, now what did we add there? A hydrohalogen, right? So I'm going to say hydrohalogenation, hydrohalogenation, like that, right? So this is how we identify it. Then 4.1.4 says name of or formula of S, right? So what they, it's S there. So now what do we need there? We're going to need a catalyst, right? So in terms of a catalyst there, what am I going to use there? I'm going to use a catalyst of so this one is going to be our concentrated H2SO4, right? So HSO4. So I can just say conc H2SO4, right? Which is our sulfuric acid there. Then 4.1.5 says the structural formula of compound T. So T, we wrote it there at the top. So the structural formula of what? Compound T. So it's already there at the top. Maybe I can just like quickly rewrite it here. 1, 2, 3, then double bond and H there. This is what we are having there. Then I'll add a hydrogen there, hydrogen and another hydrogen, then 3 more hydrogens on the first carbon there. So this is what you're going to have there. Then moving on to question 4.1.5, underneath it says compound W can be converted to T in one step, right? State besides heat one of the reaction conditions for this conversion, right? So for this conversion to happen there, we need a strong base in in alcohol, right? So I'm going to say a strong base in alcohol there, right? So this is the strong base that we are having there. Then after that, now it says here 4.2, a compound with the formula C10H2 undergoes a cracking reaction according to the equation. So we've got that equation there. So in terms of this there, they're asking us to do the mixture of the two products is bubbled in bromine water, P.2 in a darkened room, right? So define the term cracking, right? So this is we are breaking large compounds, large hydrocarbon. So it's breaking of large hydrocarbons, large hydrocarbons into smaller, more useful ones, right? More useful ones, like that. Okay, so then 4.2.2 says state one change besides a change in temperature that will be observed when the mixture is bubbled in P.2. So what we're going to expect there, right? So it means the brown color is going to changes towards to colorless, colorless. So the brown color changes from a brown to colorless. And then write down the structure formula of X there, right? So in terms of this 4.2.3, I can just like maybe quickly formulate something like more of an equation there. So what we are going to have there is from this one there, right? So I'm going to say here, what did we have there? Formula of X. So we started with something like this. Then 4.2.3, we started with something like this, and then what did we get there? We're getting that there, right? So if you can look at here, how many do we have there? We're having 4, and then we're having 10. So if I can say C6 there, and then after that, I'm going to say multiplied by the difference there. How many do I have there? From 22, 10 minus 22 is going to be 12, right? So H12, like that, right? So this is what I'm having there, right? So they're saying the structural formula there. So they're looking for the structural formula, right? So basically here in terms of this, since we're having a 2, so it's more of like 3 HR6, right? So H6 like that, right? So, but for me to write the structural formula, it's going to be something like this. So let me just like quickly write it down there. So this is what I'm going to have there in terms of my structural formula. I'm going to have a CH3. So I'm going to say an H there, an H for the first one. Then I will proceed again to put an H like that. Then here I'm going to put a double bond. Then after that I'm going to say an H again, right? So formulating what we refer to as propene, right? So meth prop propene, right? So it's going to be a propene there, right? That's the structural formula of what? Of X. Then 4.2.4 says which compound X or CH410 reacts faster with bromine, and then explain your answer. So I'm going to say X there, right? So X in terms of this, if you can look at our hydrocarbons there, so the shorter chains are more of what? Of being what? Reactive than the other ones. Then now moving on to question 5.1. So question 5.1 is define the term reaction rate, right? So reaction rate is the change in concentration of what? Change in concentration of products. So I'm going to say change in concentration, I'll just say count of or products or reactants, right? So or reactants per unit time. I'm going to say per unit time, like that, right? Then moving on to 5.2 says carbon monoxide, which is our CO gas there, reacts with oxygen, which is our O2 gas, to form carbon dioxide gas in a sealed container according to the balance equation. So this is our balance equation that you're given there. Says the graph below shows the concentration of O2 gas versus time, right? So this is our concentration you can see on our y-axis, then the time on our x-axis, right? So now they're asking at which time 10 seconds or 30 seconds is the reaction at rate higher, right? So we can look there at 10 there and then versus what? Our 20. So in terms of this, we're going to say it's 10 seconds because we can look at the gradient of the line there, right? It's going to be what? To be higher there, right? So the larger the greater the gradient, the steeper the gradient, the higher the reaction rate, or generally look at the amount of reactions, so reactants that we're having. So if we are still having more reactants there, the reaction rate is going to be what? To be faster. Then 5.2.2 says here, the reaction takes place in a 3 tm cubed container. Calculate the average rate in mole per seconds at which carbon dioxide is formed in the first 10 seconds there, right? So in terms of that, now I'm going to say what do we have there? What do we have as our equation? So we're having 2CO gas, right? So I'm going to say here container. Okay, I'm going to say the container is equivalent to 3 tm cubed, right? So 3 tm cubed. Then after that, now we're going to say, right? So your delta T, the change there, they are saying at what the reaction take place at calculate the first 10 seconds, right? So I'm going to say our delta T is equivalent to the first 10 seconds. Then after that, proceeding to that there, I'm going to say what you write there, right? So rate is equivalent to, so here they say in mole per watt per second, right? So what does that mean? It means here calculate the average rate in moles per second, right? So I'm supposed to calculate it what? In moles there, right? So for me to calculate the moles per second there, I'm going to say change in concentration all over the time for now, right? Then after that, I'm going to say delta C negative all over delta T, right? So since we're using our reactants, that's why I'm using a negative then, so that it can easily cancel out. Therefore, I'm going to say minus, then I'm going to say what did we start with there? Is final minus initial, right? So the final there, you can see what did we do there? We're starting at what is 0, 15 at initial. This is our final there, right? Then the initial is 25, 26, 27. I'm going to use 0,27 there, right? So it's final minus initial. Then remember my final I said is 0,15, then minus my initial, which is 0,27 all over. Then I'm going to say delta T, we're told for how many seconds? For 10 seconds, right? So if we're to punch our calculators, this is what we're going to get: 0. Negative 0. Bracket 0.15 minus 0.27 divided by 10. I'm getting a value of what? 0,012. I'm going to say mole, right? So dm cubed, right? So this is our concentration, remember. Then after that, I'm going to say also what did we divide with time, which is the units of measurement are going to be what? In per seconds, right? So that's what you're going to get then. Then after that, now I'm going to go back to the ratio between our oxygen and our carbon dioxide, right? So oxygen versus our carbon dioxide, right? So let's look at that. So because here we're given the one for what? For oxygen, right? But in terms of this, what are we asked there? They're saying at which carbon dioxide gas is formed, right? So in terms of this, let's look at the ratio there. So it means here ratio between carbon dioxide and oxygen is 1:2, right? Then I'll proceed to here and say our ratio there is 1:2. What does that mean? It means here, how many do I have? How many moles do I have? 0,012, then mole per dm cube per second. So is to what? Is to double, right? So if it's double this side, it means I'm supposed to multiply by 2, right? So I'm going to say bracket 0, 1, 2, like that, right? So what am I going to get there? I'm going to get a value of which is double, which is I think 0, 0, 24, right? Okay, so 24 like that, right? So 24, then this is 0, 0, 2412, yeah, mole dm cubed, I'm going to say per second, like that. So that's what we're going to get. Then after that, now we're going to say the rate, right? So what our rate there? So rate is equivalent to, so what I'm going to multiply with there is that I'm going to say the formula that we are having there. So the number of moles that we are having there, mole per dm per second, I'm going to say 0, 0.024, then multiplied by what? By the volume that is already given there. So we're told we're using this container there at the top, which is dm cubed, which is the right. So I'm going to say our right there is equivalent to, then if we multiply that one, we're going to get a value of what? 0, 0.072. Then now my answer is mole per second, right? Like that. So remember, we're asked to calculate these ones in what? In mole per second, right? Then we're done with that question there. Then they're asking us 5.1.2, 5.2.3, which reactant is in excess, right? So I'm going to say carbon dioxide, carbon monoxide, or O2, right? So I'm going to say carbon monoxide, right? So the reason behind if you can look at the mole ratio there, the mole ratio between carbon monoxide and oxygen is what? Is 2:1, right? So let's look at the one for carbon monoxide there. So carbon monoxide and oxygen. So this is 2:1, right? So in terms of that, now we're going to say, right? So O2 also is what? Is decreasing at a faster rate. So our answer there is going to be what? CO is what? Is in excess, and then O2 is also decreasing at what? At a faster rate. Then 5.2.4 says the reaction was repeated using a smaller sealed container. So they reduced the size of the container. How will this affect the magnitude of the gradient of the graph at the beginning of the reaction? Choose from increase, decrease, or remain the same, right? So I'm going to say here is going to what? To be increasing, right? So remember, now it's a smaller volume, right? So it means now within that same volume you're having a higher concentration, right? So now I'm going to say smaller volume, higher concentration, smaller volume, but what we have now, we're now having what? A higher concentration, right? So because now I conk there, now the particles are now squeezed what? Together there. So what does that mean? Is going to, we have more effective collisions per unit time, right? So I'm going to say smaller volume there, higher concentration. Therefore, what is going to happen there in terms of our gradient? We are going to have a steeper gradient, right? So that's how we attempt at that question. Then moving on to the next question, which is question 5.3, right? 5.3 is the reaction between sulfur dioxide, which is your SO2 gas, and O2 gas, right? The reaction between them, what happens there? It says here, the reaction between sulfur dioxide, which is your SO2 gas, and oxygen gas, right, takes place in a sealed container according to the balanced equation below. Therefore, we're having that like that. Then here we're having our delta H, which is negative, right? What does that mean? This is an exothermic reaction. It gives out here to the surroundings, right? So 5.31 is there. Was there a net release, right? So already I've explained this one. There was a release to the environment, right? So it's giving out there, right? So was there a net release or net absorption of the energy during the reverse reaction, right? So there, in terms of this, the forward there is a net what? A release, right? So forward reaction is exothermic, right? So I'm going to say, going this side here, what we have, we're having an exothermic reaction. What does that mean? It means going back there, our reaction is going to be what? Endothermic, right? So endothermic, like that, right? So was there a net release or net absorption of energy during the reverse reaction? So it means our answer there, I'm going to say here net absorption, right? So because the reverse reaction is opposite, which is going to be our endothermic reaction, right? So then 5.3.2 says define the term activated complex, right? So this is the unstable, transition states, unstable transition states of unstable transition state of products from, okay, steady. The unstable transition states are from reactants to products. Reactants to products. Okay, so reaction activated complex is the unstable transition state from reactants what to products. Then 5.3.3 says a catalyst which is vanadium pentoxide is added to the reaction. Explain in terms of the collision theory why the rate of the reaction will increase, right? So now we are asked in terms of what the collision theory, right? So allow me maybe to use the space at the top there. So I'm going to say there what really happened, right? So now I'm going to start by mentioning what the catalyst does, right? So a catalyst provides an alternative route, right? Provides an alternative route, okay, or pathway, right? Of lower activation energy, right? So I'm just going to write this one as EA there for time. Then after that, now more molecules have got more molecules. I'm going to say more molecules have sufficient EK, sufficient kinetic energy. So I'm just going to say EK there. Then after that, now it means what is going to happen there? They are going to have more effective collisions, okay, take place per unit time, Then after that, now what are we going to do? We're going to conclude and say then reaction rate increases, right? So as a conclusion, we're going to say reaction rate increases, or rate of reaction increases, right? So that's what we're having then. Then after that, now we're going to proceed. They're giving us the curve there. They're saying the curve X. Here they're saying curve X is the Maxwell-Boltzmann distribution curve for the reaction above, right? So we were having a catalyst there, right? Then after that, more SO2 is now added to the container at constant what temperature, right? So now it means we're increasing concentration in terms of that at a constant what temperature. How will this change affect the heat of reaction? So your delta H there, how is it going to be affected, right? So in terms of this, what we need to know is that change in concentration increases what? How will this heat of reaction affect heat of reaction, right? So in terms of this, we're going to say there what happens in terms of so our answer there, we're going to say it increases like that, okay? Then after that, they're asking us to redraw the above graph in the answer book. On the same set of axes, draw the curve that will now be obtained. Label this one as curve Y, right? So we're having that there. So what do? We increase the concentration of SO2 gas, right? So if you can see, your SO2 gas is a reactant, right? So it means now we're increasing the concentration of this one. Let me just like use maybe a different color so that it's easier for us. So we're going to have something like that, right? So this curve X, Y is going to be of higher there like that, right? So I'm going to label this one as my curve Y like that, right? So this is what we're having there, right? So in terms of our kinetic energy there, you can see if I can put our EA there, it means higher concentration. Now we're having what? More particles for Y with sufficient energy for what? For effective collisions. Now moving on to the next question, which is our question 6.1.1. The 6.1 reads there. So question 6.1 reads the equilibrium is established at 25 degrees in a saturated calcium hydroxide solution, right? Then according to the reaction, therefore we're having calcium hydroxide to give us Ca2 plus and then 2OH negative, right? Then after that, now they're asking us to state Le Chatelier's principle, right? So Le Chatelier's principle. So allow me to use this blank page here. I'm going to say when the equilibrium in a closed system, when the equilibrium in a closed system is disturbed. That's okay. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium, a new equilibrium, a new equilibrium, like that, right? By favoring the reaction that opposes the disturbance. Like that, okay. So now moving on to 6.1.2 says a few drops of the concentrated hydrochloric acid, HCl concentrated, right, are added to the equilibrium mixture. What effect does this addition have on the mass of calcium hydroxide solid, right? Choose from increase, decrease, or remain the same, right? So here I'm going to say decreases, right? So it decreases the impact that it has there, it decreases, right? So we know that what happens there is that our HCl produces H plus, which reacts with what OH to form what H2O, thereby removing hydroxide from the equilibrium mixture, right? Then after that, 6.1.3, so explain the answer to question 6.1.2 by using Le Chatelier's principle, right? So removing OH disturbs the equilibrium. So I'm going to say removing OH there, right? Disturbs the equilibrium, the equilibrium, right? Then in terms of Le Chatelier system, Le Chatelier's principle, what is going to happen? So the system shifts to the right, system shifts to the right, shifts to the right to replace OH, to replace our hydroxide ions, like that, right? So that's how we apply that one there, right? So now after that, you will know more of what our calcium hydroxide there, more calcium hydroxide therefore dissolves to produce your calcium 2 plus and your OH negative. So the mass of the solute, which is our calcium hydroxide, is also going to decrease then 6.2 there. 6.2 reads initially 70 grams. So we started with 70 grams there. So initially 70 grams of NH4HS solid there is placed in a 3 dm cubed container at 250 degrees Celsius. The container is sealed, right? So it's a closed system and the reaction is allowed to reach equilibrium according to the balanced equation, right? So this is our balanced equation there, right? So moving on to the next question, says here, the Kc values for the decomposition of NH for a solid at different temperatures are given in the table below, right? So we're having our temperatures here and then the Kc values on the other end. Then so it says is the decomposition of NH4S solid an exothermic or endothermic reaction, right? Then 6.2.2 asks us to explain the same very answer. So in terms of this, I'm going to say the type of reaction that you're looking at there is going to be an endothermic reaction, right? So I'm going to circle this one. This is our correct answer, endothermic reaction, right? So the reason behind is that increase in temperature favors the endothermic reaction, right? So I'm going to just say increase in temperature favors the endothermic reaction. There, right? So in terms of this day, so you can see your Kc value increases with an increase in what? In temperature, right? So increase in temperature favors the endothermic reaction. In this case, it's going to be what? Our forward reaction there, right? So I'm going to say there is going to be a forward reaction. Then if temperature is increased, the forward reaction is favored, right? So if temperature is increased, what happens there? The forward reaction is favored, right? So if temperature is increased, the forward reaction is favored, okay? So now the equilibrium, how does it shift? The equilibrium shifts to the right, increasing the products, right? So equilibrium shifts. So equilibrium equilibrium, allow me to finish underneath, shifts to the right? So it's going to shift to the right. Then after that, what happens there? And what is going to happen? Increase the products. Increases the products. The products, like that. Okay. So that's how we attempt question 6.2.2. Right. Moving on to the next question, which is our 6.2.3 there, right? So 6.2.3 there, what are we given in terms of that? It says here, I'll try and squeeze it here. So calculate the mass of NH4 solid that will be present at equilibrium at what? 250 degrees, right? So the first thing that you're supposed to do is to write down our Kc expression, right? So remember our Kc expression there, what are we going to have there is more of the concentration of the products or over the concentration of of the reactants, but we do not include solids, so we're only having gases there. So it means our Kc expression there is going to be concentration of of NH3 there. So it's going to be concentration of NH3 multiplied by the concentration of of our H2S, like that. Okay, so this is our starting point, right? So what I'm going to formulate there is that mention this one, maybe derive it in terms of of our X there, right? Let's assume this is our X. Then now it means in terms of our X's there, I can express this one as Kc is equivalent to our X squared, right? So now I think we're given a Kc value. If you can check there, Kc value of this one there, they said we're at at 250 degrees, right? So at 250 degrees, what do we have there in terms of our Kc value? Just let's see there, let's see there, let's see there, let's see there. Kc value at 250. Okay, so this is the one there. 250 there is going to be what? 18 times 10 negative what? 2, right? So this is what we're having there. So I'm going to substitute our Kc value by that value. 10 exponent negative 2 is equivalent to x squared, right? Therefore, what I'm going to do is to make x the separate of the formula, so which is the same as 18 times 10 negative 2, right? So to punch that in our calculator, we're going to get a value of what? Quickly, I'm going to punch this one there. So I'm going to say root of 18 times 10 exponent of negative 2 there, right? So it gives me a value of what? 0, 0.42. So I'm going to get a value of what? 0, 0.42 426 like that, right? I'm going to write it like that, right? So this is our concentration, right? So I'm going to say mole per dm cube, right? So each has got that concentration there. Then I will split my page there. Allow me to just like maybe use a different color so that it easily shows the demarcations then. So now to proceed with that question there, so now we have got the concentration of each of these, right? NH3 as well as what? H2S. Then now I'm going to say like the number of moles that are going to be produced, right? So we're going to start with the number of moles of what? Of NH3, right? So I'm going to say number of moles of what? NH3 there, right? So number of moles of NH3 is equivalent to, so now in terms of our formula, we know concentration is equivalent to a number of moles over volume, right? So I'm going to say CV there, which is our concentration multiplied by our volume, right? So what do we have there in terms of this? So we have got our concentration. I'm going to take that concentration that you calculated there for each 0.4242, then 6, then multiplied by the volume, right? So what our volume there? So the volume is given as a value of what? Of 3 there, right? So let me just like confirm there in a 3 tm cube container. So where do we have this volume there? Let me check. Multiplied by concentration multiplied by our volume. Oh, there it is, right? So this is our volume there, which is 3 dm cube there, right? So this is a 3 dm cube. So I'm going to multiply by our volume there, which is a value of 3, right? So this is equivalent to what? So I'm going to say I'm multiplied by 3 there. What do I get? I'm getting a value of 1,2727, right? So I'm going to say this is 1,27279, maybe 2 7 like that, right? 9 moles. right? So this is what I'm having there in terms of what? Of our moles, right? So now I'm going to proceed and use the mole ratio here. So to calculate the one for what? For NH3, right? I'm going to say the mole ratio between NH3 versus our NH4 and H4HS, right? So HS there, like that, right? So let's look at our balanced equation. What's the mole ratio between this one, right? So it's 1:2:1, right? So in terms of this, now we're going to say, since it's 1:1, so I'm going to say 1 this side is 2, 1 that side, right? So what do I have already here is a value of what? 1,27279, right? So on this other end, what can I have there? I'm going to say 1,27279 again, right? So this is what we're having. Then after that, I'm going to put a line again to show the demarcation. Then after that, now I'm going to proceed to say what is it that we need in terms of this, right? So now we're going to say how to calculate the initial number of moles. Remember, number of moles is equivalent to, so they're asking us to calculate the mass, right? So the mass there, right? So I'm going to say N of what? Number of moles of what? NH4HS is equivalent to M all over the molar mass, right? So already we've got this number of moles, right? So I'm going to take those number of moles and just like plug them in there, right? So what am I going to get there? So I'm going to say here molar mass of this one there is equivalent to what? So the mass that is given in terms of this, what do we have there? So I'm going to say the mass that is given. So I'll start with the number of moles. Then calculate the mass of NH4 that will be present there, right? So I'm going to say after 1:1 there, I'm going to calculate the molar mass, right? Let's calculate the molar mass there, or the number of moles there. I'm going to say calculate at equilibrium, right? I'm going to say the mass there that is given is, is 70. So given the mass of this, the initial of this one is what? Is 70 grams there, right? So is equivalent to, then I'm going to say is equivalent to what? In terms of our molar mass there, I'm going to say nitrogen is 14 multiplied by 1, then I'm going to say plus again there. What do we have there? Hydrogen, which is 4 hydrogen, so it's 1 multiplied by 4. Then I'm going to say plus again your hydrogen, which is 1 multiplied by 1, and then plus our sulfur, which is 32 multiplied by 1, right? So if we're to do our math there, we're going to get a value of what? More of like a 70 all over a 50. So if we are to divide there, we're going to get a value of what? 1,32. So it's going to be 1,3, 7272 5. Okay. Oh, yeah, I made a mistake. It's not 50, it's 51, right? So it's 51 there, right? So that's what I'm going to get there. Then after that, I'm going to say what? Moles, like that, right? So after having these moles now, we're going to proceed and say the moles that are remaining at equilibrium, right? So we need to find the number of moles that are remaining at equilibrium, right? So what I'm going to do there is that for me to calculate the number of moles that are remaining at equilibrium, I'm going to say initial moles, right? Initial moles, okay, minus the one that I actually used, right? So initial moles minus the used ones is equivalent to, it will give me what is remaining, like that, okay? So if we're having that now, I'm going to say the initial moles that we started with, I calculated them there as that value there, right? So I'm going to put that value down there, which is 1,3725, right? Then minus the ones that I actually used, right? So the ones that I actually used there, these are the ones according to our balanced mole ratio there. I'm going to say 1,27279, right? So it's equivalent there. So if I do my math there, what am I going to get? I'm going to say 1,3725 minus 1,27279 there. What do I get? I'm getting a value of what? 0,9971, right? 71 moles, right? So these are the moles that are remaining there. Then now after that, like what did they ask us to do? Calculate the mass, right? So we're looking for the mass there, right? So in terms of the mass of this which is remaining, I'm going to say the mass of this one, I'm going to say the number of moles of NH4, again NH4 HS there is equivalent to I'm going to say is equivalent to what? To M all over M, right? Then after that, now I'm going to use the number of moles that are remaining there, right? So I'm going to get a 0,9971 there is equivalent to the mass, right? So this is the mass that we're looking for all over the molar mass, which is 51, right? So therefore our M is equivalent to, we're supposed to cross multiply that one there. I'm going to say multiply by 51 there, which is going to give me a value of what? Of 5.085, right? So I'm going to say 5,085, and then I'm going to say in what? In grams there. I'm going to say grams like that. So leave it like that. Okay, now that's how we attempt that question, which is 6.2.3. Then moving on to 7.1. 7.1 is the phosphoric acid, which is this one there, is an example of an acid that can ionize in 3 steps as shown below, right? So the step number 1, step number 2, until step number 3, right? Then here 7.1.1 reads, which one is the strongest acid, H2PO4 or HPO2 negative 4, right? So in terms of this day, we are asked in terms of what the strength of these acids, right? So now which one is the one that is a stronger acid in terms between these two, right? So our answer there is going to be what? H2PO4 H2PO4 negative, right? So now why is the reason? What is the reason? So they can give a reason for the answer by referring to the data above, right? So now if we can look there, H2PO4 has got a greater Ka value, right? So I'm going to say the reason behind is that it has got a larger Ka value. Like that. Okay, so that's our reasoning behind. Then 7.1.2 says here, write down the formula of the conjugate base of that one, the H2PO4 negative, right? So in terms of that there, I'm going to say here H2PO4. So write down the 7.1.2, write down the formula of the conjugate base of H2PO4 H2PO4 negative there, right? So in terms of that, we know this one is going to go with this other one there, right? So negative 2, so this one goes with that one there. Okay, then this one pairs with that one there. So it means now our answer there is going to be what? H2PO4, then I'm going to say what? 2 negative like that, right? So then after that, 7.1.3 there, it says identify a substance behaving as an ampholyte, right, in the reactions above, right? So remember, an ampholyte is a substance that can either act as a base or an acid, right? So then I'm going to say here, what are we going to have there? I'm going to say H2PO4, right? So I'm going to say H2PO4 negative, right, can act as an acid, right? Then also can act as a base, right? So in terms of that, then after that, 7.1.4, you are given sodium hydrogen phosphate, which is this one, the Na2HPO4 solid is dissolved in water. Then here, will the resulting solution be acidic or basic, right? So in terms of this there, I'm going to say our solution is going to be basic, right? Then now we need the reason behind. The reason behind is that okay, so generally I can use this as an equation, right? So write a balanced equation to explain the answer in question like that, right? So I'm going to say we started with what? HPO4, then I'm going to say 2 negative, which is up there as a state symbol. Then I'm going to say plus our water, which is H2O in terms of a liquid, then to give us a reversible reaction, right? So this reversible reaction, what are we going to get there? I'm going to get an H2 PO4, so H2PO4, then I'm going to say negative, then after that I'm going to say plus our hydroxide ions, right? So plus OH negative, again I'm going to say what? Arc like that, right? So now it shows the production of what? Of these hydroxide, right? So generally we can see there is this production of these hydroxide ions, therefore it means our solution is going to be what? To be basic like that. Okay, so it's the formation of that hydroxide ion making the solution to be what? To be basic like that. Then Then 7.2 says here barium hydroxide, which is BaOH2, dissolves in water according to the balanced equation, right? So this is our balanced equation there is already given. Then here they're saying 100 cubic centimeters of solution is prepared by dissolving an unknown amount of barium hydroxide at 25 degrees there. Then after that, now we're saying 25 cubic centimeters. So we're having 25 cubic centimeters. Let me just like circle the volumes of these. They might come in handy. Okay, so it says 25 cubic centimeters of this barium hydroxide solution is reacted with 15 cubic centimeters of that HCl there, right? Of 0.2 mol TM cubed HCl solution in a flask according to the balanced equation, right? So we're having this barium hydroxide plus 2 HCl, then this one like that, right? Then now it says here the final pH of the solution is 12.62 at 25 degrees Celsius. Then you're asked to calculate the final concentration of that of the hydroxide ions in the ions in the flask, right? So in terms of this, it's more of like the concentration is basic, right? The pH there you can see is of a base, right? So according to our formula, I can say our pOH, to make it easy, I'll start the one with the base of a base is equivalent to 14. Then I'm going to subtract minus what? 14 minus pH, right? So 14 minus pH, like that. Then after that, now I'm going to say my pOH is equivalent to 14, right? Minus the pH that is given there. We're given a pH of what? Of 12.62 minus 12.62, right? So now what am I going to get there? Put a demarcation line there. So I'm going to get 14 minus 12.62, 14 minus 12.62, 1.38, right? So my answer is 1.38, right? So I'm going to get a value of 1.38, right? So after getting that value of 1.38, now it means now what do I have there? Now I'm having the value of what? Of pOH, right? So in terms of this one now, for me to calculate the concentration of our hydroxide ions, I'm going to say OH hydroxide ions there is equivalent to 10 negative what? pH, right? So again, I'll put a demarcation line then after that I'm going to say our OH there, OH negative there is equivalent to, then I'm going to substitute there, instead of like writing negative pH, I'm now going to put a 1.38 like that, right? So it means here concentration of these hydroxide ions is going to be OH negative is equivalent to, so I'm going to say 10 exponent 10 exponent not 110, 10 exponent negative 1.38 is equivalent to 0.01. Okay, so I'm going to say 0.041. I can say 7 like that, right? Then this is the concentration, so I'm going to say mole per dm cubed like that. Okay, so that's what we're having then moving on to 7.2.2 there, they are asking to calculate the number of moles of barium hydroxide used to prepare 100 cubic centimeters of the solution, right? So in terms of this, what I can do is maybe use a fresh page, right? So let's just like try and manipulate this page on this other end, right? So now it says here, what does it say? Calculate the number of moles of barium hydroxide using the preparation of what? Of 100 cubic centimeters, right? So we're looking for 100 cubic centimeters of this one, right? So I'm going to start with the formula for concentration, right? So concentration, I will say concentration of what? Of HCl. Concentration is equivalent to number of moles all over the volume, right? So now what I'm going to do is to make the N the separate of the formula, right? So which is going to be C times V, right? So in terms of our concentration there, let's look at the concentration that we're given there. For this acid there, you can see we're given there as 0.2. Therefore, I'm going to substitute with what? Concentration as 0.2, then multiplied by the volume, right? So let's look at the volume again. The volume is given as 15 cubic centimeters. Therefore, we're supposed to convert that one by divided by 1,000. So I'm going to say 15 divided by 1,000 there. So it gives gives me a value of what 0,015. So it's 0,015, right? So if you multiply there, what are you going to get there? So I'm just going to say multiply by 0,2. So the value of 0,003. So I'm getting a value of 0,003. Then I'm going to say in what? In moles, right? So these are the number of moles that we're having there. So after that now, I'm going to use the ratio, right? So let's look at the ratio. So the ratio between what? Our HCl, right? Okay, so HCl, and then here, remember what we got us to calculate the barium hydroxide. So I'm going to say versus our Ba, then in bracket OH, and then 2, like that, right? So let's go back to our balanced equation there. So you can see this is 1, and then the other one is going to be what? Our HCl, right? So I'm going to say, oh, there we're having 1:2, right? So the ratio is 1:2, like that, right? So if we're having a 1:2, I'm going to proceed here and say here, this is the 1, the 2, and then this side is going to be what? To be 1, right? So that's what you're having then. Then how many moles do we have on this other end here? We calculated the moles here to put 0,03, right? So I'm going to say 0,003 is 2 on this other side. What do we have there? We're having 1, right? So what does that mean? It means this one, we're going to use half of this value, which is 0,003, right? So if we were to do our math, then half of that there, so I can just say divided by 2 for my answer there. I'm going to get a value of what? 0,015, right? So these are the number of moles that we are having there. I'm going to say moles then let me just like divide my page like that. Then after that, now I'm going to proceed to say now, okay, so the final in terms of the total volume, what do we have there, right? So now what we have, if we can look at our data there, we're going to say, okay, so what do we have? We have the concentration, right, of hydroxide ions, right? So the concentration of the hydroxide ions, we calculated them there as 0,0417, right? So I'm going to say there, what we have there, we have the concentration of this OH what ions there, right? So is equivalent to 0,0 what? 417, 0,0417. This is our concentration, right? So I'm going to say a mole per dm cubed, like that. Okay, dm cubed, right? Then after that, now for me to calculate the number of moles there, right? So it means here, remember, a concentration is equivalent to number of moles all over volume, right? So I'm going to say number of moles of OH there is equivalent to, so I'm going to say CV, like that, right? So this is equivalent to what? I'm going to say here, what do I have? I have the concentration 0,0417, then multiplied by that volume, right? So if we can look there, the original volume that we're having at 15 there, and then this other what? 25. So I'm going to add these two. So I'm going to say 15 plus 25. What do I get there? 15 plus 25. 15 plus 25. What do I get? I get a 40. Therefore, remember also this is in cubic centimeters. We're supposed to convert to dm cubed, right? So if I divide that value, 40 divided by 1,000, I'm getting a value of 0,04, right? So then I'm going to say multiplied by then 0,0417, right? So if I multiply there, I'm going to get a value of what? 0,00166. I just like wrote everything there, right? So these are the moles of what? Of OH there, right? So now to proceed to the next part there, I'm going to say what do we have now. So I'm going to say now what do we have there. So I'm going to say barium hydroxide neutralizes, okay, according to the following ratio, right? So in terms of this now, if you can look at your BaOH there, BaOH2, like that, right, is 2. Again, if I can go back to the ratio again there of HCl, right? So versus HCl, we took note of that the ratio there at the top was 1:2, right? So I'm going to say 1 again is to 2. So how does it neutralize there? So it means now we are going to say half of that there, right? So now what do I have in terms of this? I'm going to say, what did I get there in terms of my my number of moles for HCl, right? So I got a value of what 0,03. So we said 0,03. So automatically maybe I can just like grab that value there because we already did it there, right? So this is the value that I'm looking for, 0.0015 there. So this is the value that I'm looking for. Then after that, now I'm going to say the number of moles there in terms of this. So I'm going to say the number of moles of what? Of barium hydroxide is equivalent to, so is equivalent to 0.00. So this value there, right? So is equivalent to 0.001668 all over the number of moles is equivalent to all over 2, right? So divided by 2, because the ratio there in terms of how it neutralizes 1 is 2. Then also I'm going to add this other one there. So this other one there is going to be the volume that we got there, this one there, right? I'm going to add it there, which is 0.0015, right? Then after adding them there, what am I going to get there? So according to this, our n is going to be divided by 2 there. Then I'm going to get 0.000834. Then I add to 0.0015. What do I get there? So I'm going to get a value of 0, so the number of moles is 0.002324. Then in moles, like that. So then after that, to conclude, then the 100 cubic centimeter solution, so is 4 times the moles in 25 cubic centimeters, right? So the number of moles in that one is 4 times the 100 cubic centimeter solution contains 4 times the moles of in 25 cubic centimeters, right? So you can say, if I can say 100 this, 100 there, divided by 25, what am I going to get? I'm going to get a value of of 4, right? So in terms of that, now I'm going to say, so now in 100 cubic centimeters, I'm going to say 4 multiplied by 0.002324, right? So for my answer there, I'm going to just say multiplied by 4, right? So I'm going to get an answer of what? So this is equivalent to an answer of 0, 0, 0 again, 9336, like that, right? So I'm going to say this is not in moles, like that. Okay, so now I'm going to proceed to the next question, which is our question number 8. So question number 8 there is define the term electrolyte, right? So we need to know what an electrolyte is, right? So an electrolyte is defined as a solution that conducts electricity, is a solution that conducts electricity, electricity through the movement of ions, through the movement of ions, like that. Then moving to 8.2 says, which ion concentration Al3 or Zn2 plus arc will increase? Give a reason for the answer. So in terms of this, I'm going to say our Al is going to increase there. I'm going to say Al3 is our answer, aluminum 3 plus there is the answer. So now we'll increase, right? So in terms of this, we can see our Al is oxidized, right? So it means Al is the anode, right? Generally this one is going to be our anode, right? So anode there. Then on this other end there, I can say this is the cathode, right? So for easier, you can refer to your data table to see that this one is more negative, and then this one is more positive. Therefore, this one formulates the anode, and then this one formulates the cathode, right? So now the reasoning behind there is just like give a reason for your answer. So I'm saying it's Al. So Aa3 plus will increase. So aluminum metal is oxidized. Aluminum metal is going to be oxidized, right? So it's oxidized there. So it means here in terms of my aluminum there, I'm going to say Al is going to formulate something like this, which is Al3 plus, then I'm going to say plus 3 electrons, right? So Al is the anode, therefore it's going to be oxidized. Therefore, all atoms go into the solution as A3, Al 3 ions there. So we're expecting these ions to be moving there, formulating our Al3 there, right? So then after that, moving on to 8.3, it says write down the cell notation for this cell, right? So then after that, now the cell notation for this cell, right? So I already mentioned this one is the anode, so therefore this one is going to be our cathode, right? So in terms of our cathode there, I'm going to say this is our Zn, right? So I'm going to say here is a cell notation. I'm going to start with my anode, which is my Al there. So I'm going to say Al. Let me just include maybe the state symbols, then their phase change. Then I'm going to say Al3 plus, then which is also what in arc now, right? Then after that, I'm going to put this salt bridge that we are having there, that salt bridge there. Then after that, I'm going to say what do I have in this other end? I'm having a Zn2 plus. Then I'm going to say a phase change again. Then after that, I'm going to have a zinc, which is a solid, right? So this is arc, right? So this is what you are having. They just refer to what to your reduction potential tables for it to be easy. Then the electrolyte in the aluminum half cell is prepared by dissolving some of the aluminum sulfate AlSO2 like that in water. Okay, so after that, they're saying calculate the mass of what Al2SO4 needed to prepare 250 cubic centimeters of the solution so that the cell operates initially under what standard conditions, right? So for this one to operate under standard conditions, we're going to start by maybe conversions, right? So look at this volume they were given as a cubic centimeter, therefore it means I'm supposed to divide it by 1,000. So if I divide it by 1,000, I'm going to get a value of what 0.25. So it's now in what dm cubed like that, right? So now to proceed, I'm going to say we'll start with the number of moles of what of Al there, right? So remember we've got our concentration is given to number of moles over volume. Therefore, what I'm going to do is to make n the separator formula. Therefore, I'm going to say Al3 is equivalent to. Therefore, if I cross multiply there, I'm going to have a concentration times volume, right? Then I'm going to say therefore this is equivalent to the concentration of this one, right? We're going to say is 1, right? So it says the soil operates initially under standard condition, right? So it means we're going to have a concentration of what? Of 1. Then multiplied by the volume that we already converted there, which is 0.205, right? So if we multiply there, you can see we're going to get the same value, which is 0.25 there. Now it's now concentration. Therefore, I'm going supposed to say mole per dm cubed, right? So this is what I'm having there. Then after that, now I'm going to proceed to the ratio. So in terms of the ratio, I'm going to say what do you have? Al2 there, Al2, Al2, SO4, SO4, then with a thread there, right, is to the other one for what? For Al3, right? So Al3 plus like that, right? So in terms of our ratio there, what we are going to say here, this one is 1 is to 2. The mole ratio is going to be 1 is to 2, right? So in terms of the ratio there, 1 is to 2, then I'm going to proceed and say, if I'm having 1 is to 2, then how many moles do I have here already? Is 0.25, right? So it means here, this side is double that one there, right? So it means here I'm supposed to say 0.25, then divided by what? Or just multiplied by a half to make our lives easier. So if we divide by 2 there, 0.25 divided by 2, I'm going to get a value of 0.125, right? So these are the moles that we're having for us for Al2 SO43, right? So after that, now I'm going to proceed to calculate the molar mass, right? So remember they said calculate the mass, right? So in terms of this, now I'm going to try and calculate the molar mass of this one, because now we're supposed to proceed to say the number of moles there of what I'm going to say Al2SO4 like that is equivalent to the mass all over the molar mass, right? So this is what you're going to have there. So I'm going to take that value of the number of moles on this side as 0.125 is equivalent to the mass that we're looking for, right? All over. So all over there, I'm going to say what the molar mass of this one. So I'm going to start with my Al there, right? So my Al there is going to be what's okay. Let me just like maybe make it easy. So for me to make it easy, I can just like maybe focus on the SO4 there. Sorry about that one. Then if I can just like maybe focus on the SO4, what am I going to get there? So if I can just say Al, okay, let me just say Al2, SO bracket SO4, then with the 3 like that. Okay, so in terms of that, now let's try and calculate the molar mass of this one, right? So in terms of my aluminium there, let me just like check and confirm. The molar mass of aluminium is going to be a value of what? There, 27, right? So it's going to be 27 there. So I'm going to say 27, okay? So aluminum is going to be 27. So I'm going to say 27 multiplied by 2, right? So since we're having two of them there, then I'm going to say plus again my sulfur. So my sulfur, I'm going to multiply 3 times 1, which is 3. So I'm going to say sulfur is 32 multiplied by 3. Then I'm going to say 3 times 4 is already 12, right? So oxygen has got A is 16. So it's 16 times 12 like that. So if we were to do our math there, we're going to say M is equivalent to what? So I'm going to multiply the so my final answer according to this, I'm going to get a value of what here I'm going to say is more of like 52, then here is 96, then here is 192, right? So if I add all these ones, I'm going to get a value of 342 grams per mole, right? So this is what I'm having then. Then after that, now it means now I can now proceed to say this molar mass there multiplied by that one there, right? So remember, we're still there at the top, right? So I'm going to cross multiply by that one. So it means our M there is equivalent to this value 342 multiplied by 0 342 not 34 342 342 342 then multiplied by 0.125, right? So if I multiply there, I'm going to get a value of what? According to my multiplication there, so 342 multiplied by 0.125 is equivalent to 42.75, right? So my answer is going to be 42.75, it's a comma there, grams like that. Okay, now we're done with question 8. Now moving on to question 9 there, it says here, the diagram below represents a cell used for refining copper. So it's a cell that is used to refine copper. Then we're having electrode there, Q, and electrode R, then this is the electrolyte, right? So then it says the unrefined copper contains zinc and only is the only impurity, right? So is this an electrolytic or a galvanic cell, right? So this is an electrolytic cell. So why there? Because we can see what do we have there? We have got a power source at the top or a battery. Then 9.2 says here, when the switch is closed, it is found after T hours that the amount of Cu2 plus ions in the electrolyte changed by 0.05 moles and 0.01 moles of Cu were deposited on electrode Q, right? Then how will the concentration of the zinc ions in the electrolyte be affected during the refining of copper? Choose from increase, decrease, or remain the same, right? So now what I'm going to say now is that from 9.1.1 I'm going to say increases, right? Increases. Then if it increases, then I'm going to say the reason behind, right? So it's that the zinc impurities, what do? They oxidize at the anode, right? So what we're going to have there is going to something like this. For an oxidation reaction, I'm going to have a Zn2 plus, then I'm going to say plus how many electrons? Plus 2 electrons. So what does that mean? So it means now the concentration of what? Of Zn is going to what? To increase there. So concentration of what? Of Zn increases. So that's the reason behind. The 9.2.2 says here, will the amount of Cu2 plus ions increase or decrease? Then explain the answer in terms of the relative strengths of the oxidizing agents, right? So the answer there is going to be what? Decrease, right? So our answer is going to decrease, right? So in terms that is that in terms of this, I can say copper is reduced at what? At the cathode too. So if it's to be reduced, our copper is to be reduced, and it is going to formulate something like this: Cu2 plus 2 electrons to formulate our Cu there, right? Then after that, now removing our Cu2 plus from the what? From the solution, right? So in terms of the strength of the oxidizing agent, I'm going to say Cu2 plus. So I'm going to say Cu2 plus is a stronger. Okay, I'm going to say stronger oxidizing agent, oxidizing agent, right? So you can always refer to your tables there to see which one is stronger, right? So then I'm going to say then what your zinc, like that, zinc 2 plus, right? So and therefore is reduced. I'm going to say and therefore is reduced. Okay, so as a conclusion, maybe I can just continue and say Cu2 plus concentration. What happens there? It decreases like that. Then moving on to the last question, which is question number 9.2.3 says calculate the change in mass of electrode R after T hours, right? So now we're looking for the change in mass of what? Of that after T hours, right? So in terms of this one there, I'm going to formulate variables, right? So in terms of our variables there, what I'm going to say here is that I'm going to use X, let me just say X. What does that give there? It gives the moles of what? Of copper oxidized. Okay, so copper we said is going to be oxidized to what? To Cu2 plus, right? Then after that, I'm also going to formulate an equation in terms of Y, which is our Y is equivalent to the moles of what? Of the zinc that has been what? Oxidized to what? To CZN2 plus, like that, right? Then after that, now what did we start with there? I'm going to say how much did we start with there? We started with 0.15 moles of what? Of Cu, right? So the Cu, I'm going to say is 0.015 Cu deposited at the cathode, right? So I'm going to say 0.15 moles of Cu were deposited where at the cathode, right? Deposited like that, right? At the cathode, okay? At the cathode like that. Then after that, what happens then? So the net charge in Cu2 plus solution is equivalent to, so the net charge of this is equivalent to, so I'm going to say the moles that are produced at the anode minus the moles that were what? Were deposited, right? So I'm going to formulate, remember I said X refers to what? To the copper from Cu, moles of copper oxidized to what? To Cu2 plus, right? So I'm going to say subtract that one there, 0, okay, how many do I have? 0.15, right? Then is equivalent to, then what we have there as a conclusion, we had also told our main moles there. Let me just like check there. Let me check there. What do we have there? So ions, they're saying here at that when the switch is closed, it is found that after T hours, the amount of Cu2 plus ions is the electrolyte changed by 0.05 there, right? So now I'm going to say is equivalent to 0.05, right? So for me to make the X the separate formula, what does that mean there? It means now I'm going to get a value of what X is equivalent to. Let me see there. What am I going to get there? I'm going to say 0, a negative there. So I'm going to say that one minus that one there. Okay. It's more of like 0.005. Just a moment, a negative 0.05 minus 0, okay, plus, delete plus 0.15. So I'm going to get a value of what? Of 0.1 moles of what? Of X, right? So these are the moles of what? Of Cu there. Then after that, which is oxidized, right? So in terms of these ones, right, there we can see the reaction ratio there is that each and every Cu or copper and zinc produces how many electrons? Is going to be what? 2 electrons, right? So in terms of this now, if I can proceed on this other end, I'm going to say what we have there. I'm going to say 2x from our equation there. If I add 2x plus our 2y, what should I get there? I'm going to get a double of whatever I started with, which is 1.5, right? So for it to be easier, I can easily eliminate my 2 there by dividing by what? By 2 on throughout there, right? So it means now what am I going to left with? I'm going to be left with what? x plus y is equivalent to 0.15, right? So in terms of this, then I'm going to proceed and say y is equivalent to, so if we're having, okay, let me just like return it like this so that it makes sense. If I can say x plus y is equivalent to 0.15, right? Then after that, now I'm going to make my y the separate of the formula, right? So it means y is equivalent to 0.15, right? But did I get the value of x? Yes, the value of x there, I got a value of what? 0.1, right? So I'm going to subtract and say 0.1 there. So our y is equivalent to, so if I say 0.15 minus 0.1, what do I get there? So it gives me a value of 0.05. So it's 0.05, right? So what were we calculating there? I'm going to say moles of what? Of zinc. So it's going to be moles of what? Of zinc, like that, right? So that way oxidized, right? So in terms of the change in mass there, so I'm going to say the terms of the change in mass there, what are we going to have there? I'm going to start by the formula for number of moles. Cu is equivalent to M all over M, like that, right? So if we're having that one there, I'm going to say the number of moles that of copper that we have there, we know now is, is 0.1 moles, right? So 0.1 moles is equivalent to M, right? So M there, which is the mass that we're looking for, all over the molar mass of what? Of copper, which is what? 65, if I'm not mistaken. Is it 65 or 63.5? Let me just like check and confirm. Yeah, it's 63.5. So instead of 65, there is going to be 63.5, right? So I'm going to change that one there to 63.5, 63.5, right? Therefore, to conclude, our M is equivalent to, so I'm going to say 0.1 multiplied by 63.5, which is equivalent to 6. What did I do there? 0.1, 0.1. Okay, so 0.1 multiplied by 63.5 SD. So it's going to be 6.35. 6.35. So your M is equivalent to 6.35 grams, right? So these are the number of moles of what? The mass of what? Of copper. Then to proceed there again, for the number of moles, I'm going to say number of moles of what? Of our zinc there again is equivalent to M all over M, right? So then after that, now I'm going to proceed to say, what do I have in terms of the number of moles there? We already know also is 0.1, right? So I'm going to say 0.1 is equivalent to the mass, right, all over the molar mass, right? So in terms of this one, what am I going to get there? I'm going to get a value of what? 65 for zinc, right? So I'm going to say 65 multiplied by 0.1. What do I get there? I'm going to get a value of what? 6.5. 6.5. 6.5 is equivalent to 6.5, like that, right? Then after that, I'm supposed to add all these two, right? So I'm going to say, what do I get there? Let me look. 65 multiplied by 0.1, 6.5. Okay. And then after that, what else do I need there? 3.25. The number of moles there for zinc is what? Did I miss something there? Zinc 0.05, 0.05 multiplied by 65 there. Okay, so there's a mistake there. Look at this there. We said the number of moles of what? Of zinc there is 0.05, right? So instead of like 0.1 there, I'm supposed to use 0.05. Sorry about that one. So I'm going to say 0.05, right? Multiplied by that there. So if we multiply there, what are we going to get? So I'm going to say 65 multiplied by 0.05. Therefore, our answer there is going to be 3.25, right? So I'm going to say 3.25 grams, right? Then what I'm going to do is to add these two, right? So I'm going to say 3.25, then plus our 6.35, right? So if we had to add there, it's going to be 10, 1, 5, then 9, 10. Am I making 3.25? Plus, let me just make use of this calculator, plus 6.35 plus 6.35. So our answer there is going to be 9,6. So I'm going to get a value of what? 9,6 grams, like that. Okay, so that's our final answer there. I'll just like erase there. So that's 9,6 grams. Okay, with that being said, thank you for watching. Hope you enjoyed the video.